Hey, this is Dr. B, and here's an overview of intermolecular forces. This is Unit 3, AP Chemistry. We can define them as the attractive force between substances, as an inter, as opposed to an intramolecular bond. Oftentimes these are shown with a solid line for a bond and a dotted line for an intermolecular force. So they're very different from the bonds themselves. And let's go through several examples. We'll start with the weak ones, and we'll work our way up with the strong ones. The weakest sort of intermolecular force goes by many names. Perhaps the simplest name is a dispersion force. But they also might appear as London forces, van der Waals forces, induced dipoles, things like that. In terms of the strength, they can be from just about nothing up to about 40 kilojoules per mole. And these are present for any substance. You will always have intermolecular forces, even if it's a noble gas. And they increase with the size of the substance in question. And that's true because they would become more polarizable. Have a look at this table here as we go from F2 up to I2. The melting points and the boiling points consecutively increase. And that's because we have to either make those solid intermolecular forces become fluid if we're going to go to a liquid, or become completely separate if we're going to go to a gas. And these big substances are more polarizable. Most people describe this as at any given point in time, the electrons may be a little off center one way or the other, and then this increases as things get larger. Moving forward, we now have these sort of substances where clearly there's a dipole. The best way to do this is to look for the elements in question and see which is the closest to fluorine, that being the most electronegative element. Oxygen's right next door, so the electrons will spend the majority of their time in the C to O double bond on the oxygen side. So it's partially negative here, partially positive here. And therefore we have a minus to plus attraction between these two molecules of formaldehyde. This is a dipole-dipole intermolecular force. It also looks relatively weak, and they increase with the electronegativity differences. So if you have two atoms in question, one is very close to fluorine or may be fluorine, and the other one is very electropositive, meaning heading down towards francium in the opposite corner, well, you're going to have a strong dipole-dipole interaction. They are partially positive and partially negative, which means they have a little bit of ionic character, and it increases as that difference in electronegativity increases. And here we have a symmetrical covalent bond. Well, this typically will only happen if the X and Y are the same element. Occasionally, you might see a problem where they have been given exactly the same sort of electronegativity value, but more often they have to be identical. And if they are different, well, the one closer to fluorine will have the electrons more towards it. And if it goes from nonpolar covalent to polar covalent to fully ionic, and this typically involves a metal with a nonmetal. Here's an example of a hydrogen bond force. This is generally considered to be the strongest type of intermolecular force, and it's a specific type of dipole-dipole interaction. Especially what it requires is a OH, NH, or H to F bond connected to something with a dipole. See this right here? This kind of describes all of it. F, O, or N to H, and in turn connected to either F, O, or N. 90% of the time you're looking for something with an NH or an OH. If it has those, it can do intermolecular forces. They are very strong dipole forces, and those are very common. Finally, we have ion dipole forces, where if you have a real cation, like a sodium cation here, in the presence of something that has a dipole, well, that's an ion dipole force. Now, take a good look at that, and you should recognize that that would just be the sodium cation in water, right? So it's oftentimes that's what it is. They can go up to 600 kilojoules per mole, much stronger than a hydrogen bond force. And really, if you see it, It's just a molecular representation of an ionic compound which has dissolved. So if you took sodium chloride, threw it in water, you'd get sodium cations with these ion dipole forces surrounding the sodium cation. There may be several of them for each sodium cation. After all, the OH2 doesn't have a formal -1 charge. And the opposite would be true for the chloride ion. So imagine the chloride ion, and these would be flipped around since the H is positive. They always do tend to look for making sure you don't have it backwards. So for this, it's OH2 plus to minus. For an anion with it, it would be the negatively charged anion in close proximity to the H's on water. As intermolecular forces increase in strength or number, lots of physical properties increase, including the melting point, the boiling point, surface tension, viscosity, and other things. For comparison, bonds, which may be covalent, ionic, metallic, or covalent networks, have bond strengths that range from 150 to 5,000 kilojoules per mole. So these are typically weaker than bonds, but there's plenty of overlap. Hey, this is Dr. B, and this was an introduction to intermolecular forces. Okay, now let's test your knowledge with some questions about intermolecular forces. And there it is. Identify the bonds or forces indicated. There's a 1 here and a 10 here, and let's do all 10. Pause each one and see if you're getting it right. Here we have an ion and something that is polar, so this should be an ion dipole intermolecular force. Here I see, go ahead and check each one. I'll try to pause. Here I see formal positive and negative charges. This must be an ionic bond. Here we have an OH, the intermolecular force to an O. That's the definition of a hydrogen bond force. This looks like it's a trick question because that's not a force at all. That looks like a nonpolar covalent bond. Here again we have the HOH, but this time the dots lead to an S, and it needs to be an O or N. They're very picky about this thing. So this would be a dipole-dipole interaction. You know, sulfur is relatively interaction negative, so that's our partial minus. The hydrogen is our partial plus. Here we have an H to S, so we're already, it can't be a hydrogen bond force connected to an O. So this looks again to me like it's a dipole force, not past tense there. Another trick question, if you will. Oh, it does say bonds or forces, so we're fine. This happens to be two different elements, so we'd have a polar covalent bond where the bulk of the electron density would be on the oxygen side. Looks like we needed to throw in a good old metallic bond there. Now the C to H bond does have a small difference in electronegativity. So this is a bond, not a force. But since hydrocarbons are essentially greasy, most people will discuss this as a kind of an exception, a nonpolar covalent bond. Oh, not much going on here. Two hydrogens with dots in between. The only thing that can really be going on is a dispersion force there. And that's some intermolecular forces and bonds. Now tell me if you agree over here, do you think it's true? As the intermolecular forces are growing stronger, will the melting point tend to increase? Certainly it will be harder to overcome that, that force in order to melt things. With the boiling point, yeah, sure, that should also increase. What do you think about reactivity? That should increase, yes? Well, no, that's a chemical property. The physical properties will generally increase, but it doesn't mean it will be more reactive, you know? I mean, as you go from helium to neon, etc., very hard to get those to react. So, probably not. Toxicity increases? I don't think so. How could you make that statement? It depends on what you're talking about. Will the molar mass increase? That seems kind of ridiculous to me. No. Will the solubility increase as the intermolecular forces get stronger? Tell me what you think. I would say I would partially agree. Things will, if you have an ionic compound, it'll dissolve more as that solute, that solvent becomes more polar. But of course, if you have a greasy substance, you don't want to increase the polarity of it. If it gets to the point where it's all oil and water, for example, they won't mix at all. So I'd say Not really. It's more like dissolves like. Finally, let's pick the substances that have the higher melting points and boiling points. Butane versus pentane. Have a look down here. Which one would have the higher boiling point and why? Okay, I hope you gave it a shot. If you said that pentane has the higher boiling point, congratulations, I agree. I hope if you needed to explain it, you would say both are only capable of dispersion forces, but the pentane molecule has more per molecule, therefore it would be overall a stronger intermolecular force. 1-butanol versus 2-butanol. Well, there is a carbon there. Take a look at that one. This is a little tougher because you have the same number of carbons, hydrogens, oxygens, same number of alcohol functionalities. The only difference is that this OH is embedded within this substance. If you made a molecular model, don't forget its tetrahedral geometry. That OH is kind of buried in there. So it has relatively inaccessible hydrogen bonds, giving it a lower boiling point. The butanol should have the higher boiling point. Iodine versus bromine. Okay, I hope you gave it a shot. Well, these are just capable also of dispersion forces. They are nonpolar covalent bonds, so there's not much going to be interacting here. But iodine is a higher melting point and boiling point. In this case, predominantly melting points. It's a fairly high melting solid, but it's more polarizable. So it has more ionic character for that dispersion force, and that'll give it a higher melting point. Finally, sodium iodide versus sodium chloride. Well, the chloride is more electronegative. It has a more ionic character and bigger differences in electronegativity. So the sodium chloride will have the higher melting point and boiling point. All right, that was some questions on intermolecular forces.